Right, we are on lesson number 8, isn't it? Yeah. Right, weights. Okay, can we go down? Yeah. Right, so gravitational force, and you can kind of see it in my little picture here. That's the force of attraction between all matter. Normally only felt when the object is really large, Earth, Moon, Sun. So for example, we know this. You learned this from elementary school. The Earth is pulling you down. This is the reason why you don't just float in space. Okay? And the weight is the amount of gravitational force. Okay, so just to be really clear, I'm saying weight is the force that's pulling you down. So I just need you to make note of these two definitions. Write these two down. Gravitational force and weight. Okay, is that them? No. Not yet? What's wrong with you? No. And what's wrong with you? Are you sure? Mm-hmm. Right, next slide. Yeah? Yeah? Well, I'm going to go to my notepad so I can go back to this. So let's find a formula for weight. Okay, so here is its mass m, and it's accelerating down, and there's a force here of W. What's the formula for force? ma. What did I say the A was for things which are falling? G, which is 9.81. So this means that the weight is equal to mg, and it's going down. So that's all I wanted to show you. The formula for weight is mg. And in fact, you really used that in the last lesson. I'm not being very careful with my minus because I'm writing in the direction sometimes. So like in that one I wrote down. Whereas here, yeah, if you wanted to say it like that, F is minus W if you want to. I'm not too worried about the sign once you're careful in the actual question. It's the most important thing. So weight equals mg. W is the weight and the mass, and g is the acceleration due to gravity. Okay, so here's a simple one. How much does a 2 kilogram book weigh? So, take your calculators out and tell me, please. What's the formula? mg. So it will be 2 times 9.81, and the answer is 19.62 newtons. Did you get that? Grace?
Yes.
You got it? You telling the truth? Okay. Now, next one. How much does this book weigh on the moon? Now, it won't be the same weight on the moon. I said, assume the acceleration due to gravity is 6 times smaller. So you don't use G. What do you think you use here? G over 6. So get the answer for me. Tell me what you get.
3.27.
Yeah, it would be 3.27 newtons. It's 6 times smaller on the moon. I tell you this. No? Yes? No? No? No. On the moon, you know this word? Yes? I tell you that it's 1 over 6 mg. On the moon it is, here it is 6 times smaller. You know this, when you see the people on the moon. Here's my astronauts. They can jump higher. There's less weight. Yeah? So here it will be 1 over 6 times 2 times 9.81, which is 3.27 newtons. Yep? Okay. Right. Wait, I typed that in totally backwards. What is the mass of the moon? No, let's just say what is the mass of the book. Yeah, let's just say what's the mass of the book. So, a 2 kilogram book weighs 4 newtons on an asteroid. Do you know what an asteroid is? Mm-hmm. Asteroid is like a big rock in space. Yeah. You know, if it hits the planet, it kills you. The problem. Kills the dinosaurs. Yeah? So what's the mass here? Who can tell me that? That should say, by the way, that should say book here, not moon, book. What's the mass of the book? 2. It's a trick question. If the mass is 2 kilograms, it's always 2 kilograms. Mass is mass everywhere. Only the weight can change. Okay? Alright. Which will hit the ground first? Yeah, but in real life, they do not hit the ground at the same time. In real life, if I drop a bowling ball on a feather right now, I will give you €1,000,000 if they hit the ground at the same time. Which will hit the ground first? The ball. Okay. So let's have a look at the calculation here. Alright, so let's split this in half. Here is the bowling ball, and let's make it a distance of 1 meter, and let's say it starts at rest. And here is the feather. It's a feather. U equals 0, and that's 1 meter. Okay. So what information do we need to know? We need U. What else do we need? We know the S. And we know the A. What's the A here? 9.81. And here, minus 9.81. So let's calculate the T. What formula can I use here? S equals UT plus a half A T squared. Oh, and the S is 1. Well, technically minus 1 because it falls 1 meter. So 2 divided by 9.81 square root, and I get an answer of T equals 0.45 seconds. Now if I do the same calculation here, S equals UT plus a half A T squared, you get the same answer. So what's wrong here? They don't hit the ground at the same time, but when I calculate it, they do. They should hit the ground at the same time. They should hit the ground in half a second, but they don't. Because of what?
Because of air.
Because of the air. Yeah, no, that's not the right word, but I know what you mean.
Yeah.
So like he said, like the air. The air is actually slowing the feather down. So my point I'm making with this example is, it's not enough just to look at the weight. Sometimes there's a force going up as well, which is slowing it. Okay. So this now is more vocabulary. The force, I often call it drive force. The force that makes it go forward is the thrust or the drive force, and the force at the back that's trying to slow it down is called the drive force. Now if you look at this picture here, which one has a drag force? The feather has a big drag force, and this one here, no drag force.
Yeah.
So in some situations, the drag force is very important. Like in your car as well. The air is what stops your car from going faster and faster. This is called the drag. So please write down these two, draw this picture. Draw this picture. Yeah, beautiful. Just draw the picture, it's enough. That's right, the shape of it, yeah. Just draw the picture. Yes. You can draw a picture of me later, okay? But the car right now. And when I say draw a picture, like draw a Stephen picture, you know, a box with two wheels on it. Don't make it, you don't need to make it nice. Yeah, you got it? Yeah, no, really, you don't need to make it nice. Okay. So terminal velocity, please note this definition carefully because it is in the exams sometimes. It's kind of a common question. Terminal velocity is the maximum velocity that an object can have when it's falling. So look, here's the picture. When he falls, he's going faster and faster. But he doesn't keep getting faster. At some point he'll reach a maximum speed. If you look at the, I'll go back here in a moment, don't worry. If you look at the graph, this is what it looks like. Time, velocity. He goes faster, 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 but then he reaches a constant speed. This is called the terminal velocity. It's basically the maximum speed. So please note the definition. Terminal velocity is the maximum possible velocity a free-falling object can have. So just the definition box, please. You got this? Yeah.
Are those still done?
No. Okay. Calculating this drag force is quite difficult. So we will make some approximations for our calculations. Can I go on? No. I just need this box, okay? Just this box. Don't draw them on, don't write this, just give me the box here. You got it?
Yeah.
I think I need to go on. It's just one sentence you need to write down. Okay, I'm going on. Okay, so you don't need to write anything here. This question is just an explanation. So my question is, and I've seen this in the exam, when you have a car and the person puts his foot down, what happens? It goes faster. But it doesn't keep going faster. It will reach a limit, you know, like so it'll go 50, 60, 70, 80, and then maybe 200 kilometers per hour. But it doesn't continue to go faster. And the question is, why not? Huh? Why does the car not go faster? Why does it reach a maximum speed of 200 kilometers per hour?
So machine is not allowed to.
No, machines works fine.
But once you see
Well, this is what happens, okay? When the car is not moving, look, when the car is not moving, is there any drag force? No. And when the car is moving slowly, is there much wind or air pushing the car back? There's a little bit. Yeah? Then what happens when the car goes faster? You can hear it. You can hear the wind hitting the car, the air hitting the car. When the car goes faster and faster, the drag force gets bigger and bigger. And then later, when the car is going very fast, the drag force equals the engine force. The two of them cancel, and there's no force left. So the car doesn't accelerate anymore. It's reached its maximum speed. Okay? So the reason the car does not continue to go faster is because when it goes faster, it gets more friction, drag force. Later, the drag force will equal the thrust force, the engine, force from the engine. And if these two forces are equal, then they cancel. And then if there's no force, then there's no acceleration because F equals ma. No F, no A, no A, no F. Okay? Yeah, I've seen this one in the exam.
So how can I do it?
Well, just understand the idea of saying, really. I mean, you can make some notes, but this is recorded, so you can watch it later. But I want to get to the calculation questions. Okay? Don't write this one down, this is just another question we need to think about. I drop a coin from a 100-meter building. How long will it take for the coin to hit the ground? Alright, well, I'll do it quickly, it's a calculation. So look, 100 meters, coin, what's the U? 0, V, we don't know, S is 100, well, minus 100, and then A is minus 9.81. So if I use S equals UT plus a half AT squared, 100, so I get an answer of time is 4.5 seconds. So my question is, if I really did do this, will it take less than 4.5, more than 4.5, or exactly 4.5 seconds in the real life? Less, more, the same. More. Why? The air slows it down. That means it will not fall as fast. That means it will take longer to hit the ground. So in real life, it will be more than 4.5. Okay? You don't need to write this down, we're just thinking here. Alright, so here's the first real calculation one, so please write this one down. A 100-gram steel ball is dropped into some oil, and the oil is 80 centimeters deep, and it takes 10 seconds for it to reach the bottom. What is the drag force? Okay. So how big is 80 centimeters? Show me 80 centimeters, somebody. How big is that roughly? Oh, way off. No, bigger than that. Yeah, about that big. So if you drop something this distance from the ground, how long should it take to hit the ground? A second. Something like this. Maybe less. Yeah. So this question, it takes 10 seconds. So that means there is a lot of drag. Yeah, let's have a look at it. So look, we have our oil, and this is 0.8 meters, and then you drop your ball here, and it takes a very long time to hit the bottom. It takes 10 seconds. So that's a lot. That's a lot. So here it is going down. Okay, so what we'll do first is, we know at least that the U is 0. We know the S is 0.8. What else do we know? We know the time. So let's calculate the acceleration. We shall use S equals UT. You know what? I'm not going to use minus. Now watch, look up carefully. I'm not going to use minus. What I'm going to do, because I'm getting tired of using minus, I'm going to call down positive, and I'm going to call up negative. So positive numbers mean down, negative numbers mean up, and you are 100% allowed to do this. It's completely halal. Okay, you're allowed to do this. S equals UT plus a half a t squared. So let me see, that's 0.8 divided by 50. Now, listen, what should the A be? If I drop it, what should the A be? What should it be? Now, what should the A be? What should it be? Come on, wake up.
0.
Wake up, children. What should the A be?
9.8.
9.8, thank you. It should be 9.8, and when I calculate it here, it's not, it's tiny, it's 0.016 meters per second squared. That's tiny. That means there's a lot of drag force. There's lots. It's moving very slowly. Like, I mean, it takes 10 seconds, you know, so it's going like this. You know, it's really slow. Lots of drag force. Now, we know, how can we calculate the force? What's the formula? We know this one, F equals ma. What's the M? What did I say it was? 100 grams? Was it? 100 grams? So, F equals ma, so that will be, now, a tiny 0.16 newtons. You say 100 grams, was it? Yeah. Now here's my question. No, that's right, it is right, it is this, yeah. What's wrong? Yeah, no. Because that's the A, that's the F. They're not the same thing. Now my question is, what is this F? Is this the weight? Is this the thrust? Is this drag? What is this F? Any ideas?
The F is
the drag?
Yes.
Nope.
Definitely
The thrust?
Yeah.
Nope. This is the
Yeah,
weight.
so-
This is the weight. No. Yes. This F, now please be careful, this F in F equals ma is always the resultant, the net, the total, the final. So this F is the total force, 0.0016 down. This is the force you get after you cancel the drag force going up. Yep.
we convert gram to kilo?
I sure hope I did. Yes, I did. Yep, that's right. Okay, so we want to find the drag force. So let's have a look here. So we have weight and we have drag. How big is the weight? Well, we know this one, it's mg. How big is the drag then? Well, you know that W minus the drag, that should equal F. The force going down minus the cancelling force going up should equal F. So you can know that the drag will equal W minus F.
You remove the, okay.
So this is your formula, drag equal weight.
Kind of, it's not really a new formula, it's more just an idea. Like for example, if I say there's 10 newtons this way, and then I'm pulling back with 7 newtons, then really there's only 3 newtons this way. Yeah? So like if I push this way with 10, and then he pulls away with 7, then total there's only 3, you know? It's not really a formula, it's more just natural idea. Yeah. Now, why did I say roughly 0.974? Why did I not say exactly? Yeah, why did I say roughly? Why not exactly? Well, the reason is this: the drag force is not constant. At the beginning, there's no drag force because the ball is not moving yet. And at the end, there's maximum drag force. So this really is only an average. Think about the example with the car. When the car is moving slowly, is there a lot or a little drag force? A little. And when the car is moving fast, there's lots of drag. So this answer really is an average.
Because the drag is constant.
Because the drag is not constant. Because because the drag is small at the start and big at the end. So it's only an average, roughly. Okay. At the beginning, in fact, the drag is 0, and then when the ball starts to move in the oil, then the drag increases. Yeah. You get the idea? Yeah? Yeah? No.
It means that the ball
Yeah.
drop very fast, so the ball
Yeah.
drop very
Big.
number is very big.
Yeah. So like if you give me the, so like if you look here, so if I put a ball here, it will fall down, right?
Yeah.
At the start, there's only the weight. And then when the ball moves in the water pushes up.
Yeah.
If the ball moves fast, do you get more or less drag?
More.
More. If I try to swim really fast, I get more drag force. So this answer here is only an average because at the beginning, when the ball is slow, the force is small, and then at the end, when it's going fast, it's bigger. So this is like an average. At the start it's 0 and at the end maybe it's like, I don't know.
0.09.
Did I mistype it? No, I think it's okay. You happy or unhappy? Or you don't know? You're a little happy. Point 1. Drag is weight minus force, which is weight. What's the weight? 0.100 times 9.81. The weight, this is the weight, not 0.1. You put in the mass. Okay, can I go on to the next example?
Yes.
Yeah, okay. Okay, but I'll pause the video and everybody looks dead. I'll give you 5 minutes, really, only 5 minutes. You can go get some water or whatever you need to do, and then I'll just continue with the next example, okay? So, seriously, 5 minutes. Go. Actually, there was no other example. That was the last example. So what I'll do is I'll stop the video for the first lesson, and then we'll start the next lesson when people come back. Okay? So I'll leave this up on the screen if you want to take a picture when you come back.